Hello from the Forcetronics YouTube channel. Welcome to Tips on Improving ADC Measurement Accuracy and Resolution, and this is part one and most likely a four-part series. And I'm real excited for this series because for selfish reasons, whenever I do tutorials like this, I'm always reminded of things I forgot myself when I'm doing my research. So anyway, before we get started, check out Forcetronics.com for information on Forcetronics services. We also have some low-cost Arduino boards that are authentic, so check those out. If you like what you see here, please subscribe to my YouTube channel or hit the thumbs up for this video. And if you need any PCBs made, check out PCBWay. That's where I go for all my PCBs, and we'll actually see a PCBWay board in part two. All right, enough of that. Let's get started. Okay, so part one is going to be more of the basics. What is measurement resolution, accuracy, and what are the types of errors you can see in your measurement, and how are they all related? What is the importance of understanding the ADC reference voltage and utilizing the whole range of the ADC? We'll talk about that in this video right here. In part 2, 3, and 4, we'll get into some more advanced topics. In part 2, we'll talk about handling low power or weak signals. In part 3, we'll talk about, after you already made your ADC measurements, techniques and software to increase resolution and possibly accuracy. And then in part 4, I really haven't defined what I was going to talk about yet in part 4, but there's plenty of content. You could really, for this topic, you could do a 20 or 30 part series, really. But don't worry, we'll have plenty of content in part 4. We may even do a part 5, who knows. Okay, let's talk about accuracy and error and precision, and then next we'll talk about resolution. So accuracy, measurement accuracy is basically how close are you to representing the true signal in your measurement. And precision can be thought of as repeatability. So if we have a signal that's not changing, how repeatable is our measurement? And I love this dartboard analogy for these two topics. Think of, we're trying to hit the circle in the middle. So think of that as the true value of the measurement we're making with the ADC. So on the top left, we have an example of low accuracy and poor precision, right? Because our darts or our measurements are all over the board. We do get one in the middle, but it's sort of just by chance. If we go over to the right, we're not accurate, we're off the mark, but we're repeatable, right? So we're constantly making the same area for the dartboard or the same measurement, even though it's not accurate. Here, we're accurate, but we're not precise or we're not repeatable. So if these were measurements and we were to average them together, we would get this, middle value, the true value, but we're not repeatable in our measurements. And then of course, finally, we have high accuracy and high precision or high repeatability. What's important about, I'm not going to talk much more about precision after this, but what's important about precision and accuracy is they can tell us the types of error we're seeing in our measurement, right? And it's important to understand the type of error you're seeing because then you can take actions to correct it. Some of those actions we'll talk about in this series, or you might know what the source of the error is. So we can have random error caused by random noise. And often this takes, a Gaussian distribution. So if you're familiar with statistics, if we have random error in our measurement, and you're going to have random error in every measurement, and we plotted that random error, it would take on the Gaussian distribution. So if we did 1,000 measurements and plotted them in a Gaussian distribution, we should see something start to form a Gaussian curve, assuming we don't have other areas of error. That brings me to the other types of error, that's systematic error. This is sort of what I would call constant error. So if your voltage reference is not what you think it is, and it's always that same value, you're going to have systematic error. And if you don't know what a voltage reference is, don't worry, we're going to talk about that. So if we look at our dartboard, here we have low random error, but we have high systematic error. Here we have low or no systematic error, but we have random error. Here we have both. Well, actually, this is more random error, I guess I would say. Anyway, let's look at this diagram. This is another way to look at the types of error. So if we think of this truth as our real value that we're trying to measure, this arrow would be our systematic error, right? Let's pretend the mean, this dotted line, is our measurement. This would be systematic error if we keep making the same measurement and we're getting the same value. Random error takes this Gaussian curve. So if you're not familiar with statistics, you can always Google it. But the idea is, let's say we had no systematic error and this mean or this dotted line was the true value we're trying to measure. Well, if we did 1,000 measurements, some of those measurements will land on that true value, but others won't. They'll eventually take on this curve, this Gaussian curve. And the fatter the Gaussian curve, the higher the standard deviation, the more random error we have. The skinnier it is, the less random error we have. Okay, so this is sort of understanding, random versus systematic error. And if we know what types of error we have, so for instance, say systematic error, if we have constant error of a certain value all the time, we can put, a correction factor in our software and just eliminate the systematic error. Now, things typically aren't that simple, but that's just one way. Or we could use averaging of our measurements to get rid of the random error. And one thing to note, though, how things get more complex is if you have a complex design, a lot of times there's multiple things happening in your circuit, and those multiple things can affect what type of error you see at any given time. So for instance, let's say you had Bluetooth on your design, and for whatever reason, you made the mistake of putting your antenna, your transmitter, right near where you're making your ADC measurement. Well, that can cause error, right? That can cause systematic and random error. But let's say sometimes you make measurements and the Bluetooth is transmitting, but sometimes you make measurements and it's not. So you'll see the error from the Bluetooth signal come and go in your measurements. Often error is not that simple as constant systematic or some kind of constant random value. And if you have a complex design and you made 100,000 measurements and you plotted those measurements, you might see multiple Gaussian curves at different positions because you have different types of systematic and random error depending on what the circuit is doing at that time. Okay, and lastly, quantization error, and I sort of cheated on that. Quantization error is really just a subsection of systematic error, but quantization error is caused by limitations in resolution, right? Resolution is not continuous, it's discrete, but an analog signal is continuous. So depending on our resolution, we're not going to be able to represent the true value of that signal, and that's quantization error. So you could have ideal accuracy, but if you have low resolution, you're going to have high quantization error. And that's a great lead into talking about resolution now. So ADC resolution. ADC resolution, a lot of people think resolution and accuracy are sort of one and the same. They're not. Resolution is your ability to resolve a signal. So look at this ruler analogy, right? I could have a centimeter ruler, I could have a millimeter ruler. Well, if I'm measuring a length that's a little less than 2 centimeters, a little more than 2 centimeters, I really can only tell you that it's 2 centimeters, right? Because I don't know how much more, how much less. But if I'm using millimeters, and it's a little less, let's say it's 18 millimeters, I can say 18 millimeters instead of 20 or 2 centimeters. Or I could say 22 millimeters. So you're getting more information about the true value of the signal. More resolution, the better, right? Now, there is limitations, and I'll probably talk about this more, but you could have very high resolution, but if you have poor accuracy, that resolution, that high resolution, not all of the bits may be useful. And vice versa, you could have ideal accuracy, but low resolution, and you're not going to be able to represent the true value of that signal. Resolution for ADCs is represented in bits, and bits is basically, related to binary counting or powers of 2. So for instance, if we have a 2-bit resolution ADC, that means that ADC can measure 4 distinct states. So let's say our ADC has a range of 5 volts to 0 volts. Wherever the signal lands, we're going to either represent it as the ADC is either going to return 0 volts, 1.6667, 3.3333, or 5 volts, right? So even if the signal is in between here, we're going to get 3.33 or 5 volts. Now, if we were to go up to 10 bits of resolution, there's not actually ADCs out there that are 2 bits. 10 bits, 12 bits are common ones. But if we go up to 10 bits of resolution, that means we have 2 to the 10 possible values, or 1024. So if we wanted to figure out what our resolution is, we would take the range or the scale of our ADC, and we would divide it by the resolution. Now, it's important to note, this stupid thing won't disappear. It's important to note, we don't use 1024 values because one of those values is 0. So we would divide 5 volts by 1023, and that gives us about 5 millivolts. So that's our ability to resolve a signal based on the ADC's range and resolution. Now, quantization error, which I mentioned on the previous slide, is basically this value, for a 10-bit ADC in a 5-volt range, it's this value divided by 2. So it would be 2.45 millivolts would be our quantization error, meaning that's the max value. If we had ideal accuracy, that's the max value of error we would have with limitations in the resolution. So if we look at this 2-bit example, if you have a value that falls right in between 5 volts and 3.33 volts, our ADC is only going to return either 5 or 3.3 volts. So if we're right in the middle, that's the maximum amount of error we'll have. Now we could be closer to 5 volts and return 5 volts, and there's some quantization error, but the max quantization error is right in between 2 levels. Okay, makes sense? So that's accuracy, resolution, error, and we also talked about precision. So those are key things to understand with an ADC when you're picking out an ADC. Now let's talk about an ADC voltage reference. And I'm going to talk about this more in terms of using an ADC on a microcontroller, but a lot of this is applicable to, an ADC on an IC. Now, an ADC's measurement range and what it uses to compare signals to is based on the voltage reference. And typically the lower range is defined by ground. Unless you have a differential ADC, then you might have 2 voltages, the 2 different measurement lanes for the ADC. But let's just pretend we have a single-ended, and that's what we're going to mainly assume in this series. We'll talk a little bit about differential measurements, but mainly we're going to talk about single-ended measurements. So with a single-ended measurement, one side of our measurement range is ground, and then the high value, the top value, is defined by our voltage reference. Now, if you're familiar with Arduino and making ADC measurements with Arduino uses VCC, or the power supply going to the chip, as the reference voltage. So if you have an Arduino Maker Series, Arduino Zero, with the SAM-D21 chip, you're going to have a 3.3 volt ADC range, 0 or ground to 3.3 volts. If you have Arduino Uno, you're going to have a 5 volt, and that's going off the power supply for the microcontroller. There's other options, though, typically for an ADC, what to use as the voltage reference. Sometimes the ADCs or microcontrollers will have a built-in voltage reference that you can use. And that built-in voltage reference will be, typically lower than VCC, always lower than VCC. Or a lot of times they'll have an external pin where you can feed in your own reference voltage. Of course, this reference voltage has to be lower than VCC. And we're going to talk about reasons why we would want to use different options for our voltage reference. But one thing to note that we're about to show is often, depending on what accuracies you need, if you're just trying to get the general idea of a signal, where it is, you can use VCC as your voltage reference for your ADC. But if you're trying to make more accurate measurements, VCC is not a good thing to use for your reference signal, and let's see why. Okay, so here you're looking at a colorful display from an oscilloscope. So an oscilloscope basically makes voltage measurements over time. And what I'm doing is measuring 3 different voltage values. And these voltage values can be thought of as the reference voltage for an ADC. Now, I mentioned how a reference voltage defines the range of the ADC, but typically the reference voltage is used for calculating the value that's being measured. So if you have error in your reference voltage, it's going to translate directly to error in your measurements. So for instance, for a successive approximation ADC, which is typically what you see in a microcontroller, you're basically dividing your reference voltage down and comparing it to your input signal to get what the digital measurement is. And we'll talk more about that in part 2. So a clean reference signal, ADC reference, which is called AREF on Arduino boards, is key to making accurate measurements. So what I did here, and this is more trying to show random error versus systematic error, but the idea here is I measured 3 different voltage values that you could use as your reference voltage for an ADC. And what I did is I zoomed in real close on them. So we're looking at 100 millivolt per division. So this first one is a DAC value from a 12-bit DAC. It has fairly filtered output, but you can see some constant noise on it, varying noise. The other one is a 3.3 volt value from a linear regulator on an Arduino Zero. So linear regulators, and this is not a tutorial on voltage converters, but linear regulators are going to be less noisy than switching regulators. And that's what we're looking at next, a DC to DC converter, which is a switch mode power supply. That's what's on the bottom here. So you can see from a random noise perspective, they all look fairly similar. But from more of a systematic or non-Gaussian random noise perspective, we can see a lot more bigger spikes on the DC to DC converter. And this is not surprising based on the nature of a DC to DC converter design. Here's the same measurement, but what I did is the oscilloscope has a high resolution feature, which basically just means it averages some of the measurements together. When you do that, you can see the random noise disappears, right? And a lot of times, random noise is true Gaussian. It doesn't show up much in your ADC measurements because your ADC measurement is a measurement over time as well. So the faster you do an ADC measurement, the more likely you are to see random error. But if you do sort of slower ADC measurements, a lot of that random error just gets canceled out anyway. But here we can still see clear spikes from the DC to DC converter. So that's why you never want to use a switch mode power supply as your voltage reference for an ADC. Another thing to note, another reason why using VCC is bad, because you can look right here, this green one is essentially VCC on an Arduino Zero board, and it looks like a very clean signal, which it is. But another reason why it can be bad to use it is the linear regulator is not going to have an exact value. So let's say it's supposed to be 3.3. Well, it's really going to be 3.303. So it might have 5 millivolts of error or 10 millivolts of error, and maybe that systematic error is always there, but you think your reference is 3.3 volts, but it's really 3.31, right? So that systematic error is always going to be there. But another thing, remember we talked about a circuit is always doing different stuff. A power supply has a spec known as line regulation and load regulation. And line regulation is based on the variance of the input power. So if you have a varying input going into that linear regulator, its output value is going to vary a tiny bit. Load regulation is, let's say your circuit is not drawing that much current, so your output is going to be at some value. But let's say all of a sudden the current draw shoots up. Well, that power supply output is going to change a tiny bit. And so the idea is if you're using that as your reference for an ADC, you're going to have this error come and go, and it's going to be unpredictable when it comes and goes. So you're not going to be able to, put a fudge factor in your software or something like that. So that's another reason why you want to avoid VCC. Switching power supplies are real noisy. They're going to cause error, but even linear power supplies, due to line load regulation specs, can change and add error to your measurement. And here's an example of I'm trying to represent, let's say, load regulation error in a power supply. So here's an Arduino Zero making 12-bit measurements, right? And I feed in an external voltage reference. I'm not going to go over the code for this, but I'll post it on my blog if someone's interested. VREF, what I did was VREF external signal from a waveform generator is 3.3 volts DC, right? So this will be a fairly clean signal. But what I did is I added a square wave on top of that that's only 50 millivolts peak to peak and has a frequency of 10 hertz. And I'm doing this to simulate sort of load regulation error. So what I did is I measured a value that was 1 volt. I measured it 500 times. Notice the readings, though, are at one value, then they shift, then they go back up, then they shift. So this is trying to show if you have a varying voltage reference, let's say from load regulation, it's going to affect your measurements directly, right? And we can see in this measurement, you can see there's random error, right? The measurements vary a little bit. Here's an outlier, but you can clearly see the varying systematic error from the varying voltage reference, right? So anyway, the whole point here is be aware of your voltage reference. And let's talk about ADC range and scaling. And after this, we'll talk more about options for voltage references. So we mentioned how the voltage reference defines the range of the ADC, right? And the resolution is defined by how many bits the ADC has. And we talked about, how to calculate what is your resolution in voltage based on your range and your resolution. So let's say we have an ADC voltage range of 5 volts, and it's 4-bit. So we have 16 distinct levels, right? Because 2 to the 4 is 16. Let's say we want to measure a signal from an analog sensor, an analog output from a sensor. But let's say that sensor, its output only goes from 0 to 2.5 volts. So that means we're not using the whole range of the ADC. So if we make a measurement on this sensor output, we can only represent it in 8 different values, right? But if we can better scale our analog measurement to the whole range of our ADC, we're actually going to get better resolution, right? We're not going to increase the bits of resolution, but we'll get better, more resolved measurements of the actual value. So for instance, let's say we took that same sensor output and we had a op amp with a ×2 gain. And I'm assuming people watching this have a basic understanding of op amps. So we could send this analog signal, this one over here, through our amplifier, amplify it to 5 volts, right? 0 to 5 now, all of a sudden it's its range. That matches the ADC. Now we have that same signal and we can represent it with 16 unique values instead of 8. So you can see the importance of scaling your measurement to the ADC, right? And there's different ways to do that, and I'll talk about more. We can, amplify or step down this signal, or we can change the range of our ADC to better scale to the measurement we're making, or the signal we're measuring. Now keep in mind though, there is trade-offs, right? So if we use an amplifier is going to introduce some level of error. It might be very small. Some microcontrollers actually have built-in gain amplifiers, so you can actually do this inside the microcontroller. Okay, and this is basically talking about what I just said. So a lot of times ADCs will have multiple options for built-in internal references, so you don't have to use VCC. So for instance, the SAM-D21, which is used on the Maker series for Arduino, it has 4 different internal reference values. Now these values will always be lower than VCC, but you have some options to scale your measurement range to the signal you're measuring. And a lot of times you can change these reference values in real time. So you can make a measurement on one ADC pin with one internal reference and then change the internal reference for another measurement. Another thing you can do, as I mentioned, is you can use an amplifier to step up a signal. Let's say you have a signal that's above your ADC range. You can use a voltage divider to step it down. And we'll talk about some of the pitfalls of using a voltage divider with an ADC in part 2 to watch out for, but that's something you can do. Or you can use an external reference that matches the range of the ADC you're looking for. And they sell external voltage references, and here's an example of one below. Or you could use an external DAC. Now, a DAC typically needs a voltage reference as well, but using a DAC as your input voltage reference allows you to scale that value in real time. So depending on the signal you're measuring. Okay, once again, they sell external voltage references. They're going to be low noise. They're going to be a constant voltage, so they're a much better way to do a measurement versus using VCC. Now, they're typically basically a diode. And they make some more advanced ICs for voltage references that you can check out. But here's a setup for one. But basically, you have a resistor, and the diode's going to have a defined amount of current that'll flow through it. That means there's going to be a defined voltage drop across it. And then this resistor, the voltage drop across the resistor may vary, but it'll always stay constant here. And so that's what you would use as your voltage reference for your ADC. And then you can even see they have ways to make it so you can vary it, right? If one of these was an adjustable resistor, you could actually adjust the output voltage of your voltage reference in real time to match the signal that you're measuring. Okay, that's it for part 1. We covered a lot. So if you have any questions, use the comment section below. If you have anything to add, anything maybe I misspoke or missed something, please use the comment section below. I love when people, add value to the videos. All right, I'll see you back here for part 2, and thanks for watching.